Pansy the Answer Dog and I are going to work on our second Camtasia for the Anatomy and Physiology course. This is topic 2. It's going to be the subject of quiz 2, and we're working on the chemistry of life. I suspect some of you are a little bit intimidated by the prospect of having to deal with chemistry, but and I also suspect that many of you, if not all of you, have a weak background in chemistry, and that's okay. It is what it is. But it turns out that physiology has a huge dependence on the chemistry in the human body. So we really need to address these things in order to be able to talk intelligently about a number of the processes that go on within our bodies. Once again, special credit to Professor Karen Montgomery, who assisted me, and her help has been just so appreciated and helpful in getting this project together, this second topic. So here we go. The atom is the smallest unit of elements. There are 3 subatomic particles. You'll notice that in your version of the PowerPoint, some of these things are going to be missing. You want to fill those in. I'm going to move along as though they're there because I can't remember which things are missing. But you can always pause this recording so that you can get what you need from this recording. One of the components is the electron. The electron has a -1 charge. This is sort of an arbitrary charge. We're not going to work with units on this. We'll just consider it a -1. It has an extremely small mass, almost, in fact, usually it's not even considered when you consider the mass of an atom. And it orbits around the nucleus of the atom. Protons are found in the nucleus. They have a +1 charge, so if you have 1 electron and 1 proton, they will offset each other exactly so that the overall charge would be 0. They have a much more substantial mass, and their mass is considered to be 1 atomic mass unit. That's what AMU stands for. By the way, you're not going to have to really worry a lot about these units. We're not going to be using them a lot in this class, but just for the sake of being relatively complete, we'll go through this. Neutrons don't have any charge. Their relative mass is very close to that of a proton. It's not exactly, but it's very close. And they're considered to be 1 atomic mass unit. And then we have elements. The atoms of elements are all nearly the same in attributes chemically. And I think I should probably clarify that a little bit. Some of you are probably aware of that, or of the opinion with whatever background you have, that the atoms of a specific element would all be exactly the same. They're not actually. There are things called isotopes that have different masses, and in fact in some elements there might be a radioactive isotope. For example, carbon has a radioactive isotope. It's not of a lot of consequence for us, but it does have usefulness in the study of organisms and their histories. The atomic number for an element would be equal to the number of protons found in the element, and if an atom is neutral, the number of electrons will equal the number of protons. So here are some elements. Hydrogen, I'm sure you've all heard of hydrogen. Carbon, and I'm sure you've heard of that as well. We use symbols for those, typically a single or maybe 2 letter symbol for each of the atoms, or each of the elements rather. Molecules are formed when atoms interact and combine, and we can have relatively simple molecules. For example, carbon dioxide. You see that the C is for carbon, oxygen is O, and the 2 means there are 2 of these oxygens combined with this 1 carbon. You also notice that the name carbon dioxide, di, if you'll remember your zoological roots, means 2. Carbon dioxide is an important gas. It's one of the respiratory gases. By the way, the chemistry that we are going to discuss in this PowerPoint will be focused on the subject of physiology. We're not going to go off into chemistry of obscure non-organic or forms, because they're not really pertinent to the study of physiology. Molecular mass is going to be the algebraic sum of the atomic masses, and simply in this case we have one carbon. Carbon has a mass of 12 atomic mass units. Oxygen has an atomic mass unit mass of 16. There are two of them, so we multiply 2 times 16. We add these numbers together and we get 44 atomic mass units for one molecule of carbon dioxide. Here is a model of a water molecule. So we've been talking about formulas, chemical formulas of molecules. Here we have a representation of the physical structure using the spheres connected by bonds. In this case, the red is oxygen, and this gray is hydrogen, and these little connecting pegs are actually bonds between these atoms. And if you were to measure the angle between these, it would be predictable. It would be about 104 degrees. I think it's actually 104.5. Here is a little more complicated model because it's a larger compound. This is alanine. Alanine is an amino acid, and so here we have carbon in green. The blue is nitrogen, the silver is hydrogen, and the red is oxygen, as before. Maybe you can tell from this, these spheres have slightly different sizes, and that's because in reality these atoms have different sizes. Here we have a space-filled model for vitamin C, a rather important component of our diet. So the molecular mass, you're probably thinking, why do we even care? The molecular mass is a way of estimating how many particles there are in a solution, and that turns out to be really important. For example, if you go to the hospital and you get an IV drip, they always make sure that the concentrations are appropriate, or else you could kill the person if you gave them the wrong concentrations. And we use them to estimate concentration the same way that you would with a paper bag full of apples. If you know the weight of the average apple and then you weigh the whole bag, you can tell how many apples there are in the bag without counting them. And since we really can't count molecules, if you measure the mass and you know what the mass of one molecule is, you can tell how many molecules there are in a given amount of material. So concentration is important, and the concentration is the number or amount of a particular substance per volume. That has to be maintained in the body in order to maintain normal health. So really important concept. 99% of the human body's mass is made up actually of only 4 elements: hydrogen, carbon, oxygen, and nitrogen. There are other things there, and all of the other things are necessary. That 1% is not trivial, but this kind of is staggering to feel that almost all of your mass is just 4 different elements. Energy is really important for life. We use energy for a number of things, a number of processes within the body, within the cells, and the energy that we use comes from chemical bonds. So it's a little bit, it is rather important to have sort of a grasp of how many bonds the different elements can form. And hydrogen can have 1 bond, and that's it. Oxygen typically has 2 bonds. Carbon can have 4, and nitrogen has 3. And these are the 4 elements that make up 99% of our mass. So they're sort of very important in terms of the kinds of compounds they can form. So bonds occur in 2 varieties, and one of the things that I hope you'll appreciate as we go through our course is that when scientists put things in categories, the categories are defined, but not all things fit nicely into categories. There are some things that sort of straddle the boundaries. Now, this is because the categories are artificial. They're constructs made by humans, and so in nature, all things don't fit nicely into different categories. Some things are sort of across the boundaries. However, we'll look at two major kinds of bonds. One kind of bond occurs when elements are shared between two atoms of the same element. If they're shared by the same element, neither of the atoms has more claim over the electrons than the other, and so we end up with a nonpolar covalent bond. These are actually the most common kind of bonds and in organic compounds, and we're going to see some examples of that as we go along here. Sometimes the electrons aren't shared equally, and a good example of that would be water. The reason water doesn't share the electrons equally is because the oxygen has a greater affinity, or sort of attracts the electrons of a bond more strongly than the hydrogen does. So it's an uneven sharing of the electrons, and as a consequence, the hydrogen end of the water molecule ends up with a positive charge, and the oxygen end of the molecule ends up with a negative charge. And that means that this molecule is going to be a little bit like a magnet, and the positive end of one water molecule will be attracted to the negative end of another. Okay, so there are a lot of different kinds of molecules that have polar covalent bonds. Water is particularly important, and the reason I bring it up is that it makes up a majority of our mass. It's used in transporting materials through our blood, and so it's hugely important as a transport vehicle. Some organic molecules have a slightly polar covalent bond, and those that have a slightly polar covalent bond will be attracted to water. So sometimes two atoms of different materials, two different elements interact, and one of the atoms is attracted to electrons more strongly than the other. And when that happens, sometimes the electrons are actually exchanged. One atom gives up an electron, or maybe more than one electron, and the other atom takes those electrons. And typically metals give up the electrons, and nonmetals usually accept the electrons. And then when that happens, you end up with particles that have a charge. The one that lost an electron, if it loses just one, will have a positive charge, and the one that gains the electron will have a negative charge. And then you have these two charged particles, and they attract to each other electrostatically, but it's basically a lot like a magnet, and so they stick together. Excuse me. The exchange of the electrons happens because with that exchange, the stability of the atoms is increased. And the atoms of ionic compounds are held together because of this electrostatic attraction. Actually, they're called ions at that point. They're not referred to as atoms any longer. Okay, so you're probably thinking, why is he going through this? Why do we care? What a pain. So what we're going to do is look at water. Okay, and remember, water is an important compound to consider here because that makes up the majority of our mass, and it is the way we transport things. So water is going to have polar covalent bonds. We already discussed that. In addition to that, there is something called hydrogen bonds that occur between adjacent molecules. We're not going to go into a lot of detail here, but the hydrogen bonds actually are kind of important because they also occur in proteins, and they help hold proteins together and hold protein molecules in their shape. So a hydrogen bond occurs when a hydrogen of one water molecule, which has sort of lost, that hydrogen has lost its electron to the oxygen somewhat, not completely, but somewhat, sort of has a positive charge. And when it comes close to the adjacent water molecules, there are unshared pairs of electrons on the oxygen, and the hydrogen associates itself with those. That's called a hydrogen bond. It's a pretty strong bond, stronger than a polar bond. So the water molecules are held together by two things, the polarity and by the hydrogen bonds. And this means that water molecules are rather difficult to separate. This unusual characteristic of water makes it really good for a number of things. One of the functions for water is that it is a solvent for us, especially for ionic compounds and for polar molecules. And it forms solutions, and these solutions are the way that we transport things within the body. That's a big deal. That's how you carry electrolytes through your body, in your blood, so that the cells have the appropriate electrolytes available to them. And the same thing for proteins and sugars. Not so much for lipids. A second thing that is kind of important here, as I mentioned, water is the dominant material within our body. It means that our body is primarily in a liquid state, and you notice I not Maine, and for that matter, not actually Rhode Island either. But there are three physical states of matter. There's a liquid state, there's a solid state, and there's a gaseous state. And primarily being liquid has a huge impact on reactions and transport of materials through the body that make it possible for us to stay alive. So it's good for reactions because the concentrations are high in liquids, much higher than they would be in gases. Liquids can be pumped, solids can't. And because these molecules are not fixed in place as they would be in a solid, they move around and we have lots of collisions between molecules. And collisions between molecules, I mean, if you drive a car, collisions are not good things to have. But when you have molecules, if you want them to react, they have to collide with other molecules. And those collisions result in reactions that allow us to live. We're going to transport material through the body, and about 92% of your blood is water. So this is why I've been stressing water so much. One of the things we find in solutions is that likes dissolve likes. And what that means is polar compounds are good at dissolving polar materials and electrolytes, and not so good at dissolving nonpolar compounds, which becomes sort of a problem for us. Things that go into water solutions are called hydrophilic. Okay. So it's good news and bad news. And the good news is that electrolytes and slightly polar compounds go into solution, but the bad news is that lipids and the respiratory gases, among other things, but particularly those, aren't very soluble in water, and so distributing them becomes a real problem. And yet we do have to distribute them, obviously. So for example, we'll ask Pansy the answer to it because she knows the answer to this, because she's wicked smart. How would we get these respiratory gases to be distributed through the body if they don't go into solution, Pansy? And Pansy says, oh, right, we have cells, specific cells, to transport the respiratory gases. And the name of the cell is, right, red blood cells. Actually, Pansy's favorite word is rough, but she has to expand her dictionary here when we're doing these Camtasias. So water molecules are both cohesive and adhesive, and some of you are probably thinking, okay, what is this all about? Cohesion means that water molecules stick together. I already told you that they form hydrogen bonds and that they're polar, and therefore they do stick together. And this sticking together thing, it turns out to be really important, especially for breathing. It forms surface tension. And I'm going to go into sort of a discussion of surface tension in class with you. For now, just accept that it is a big deal, that the molecules, one molecule of water adheres to another molecule, and so they don't stretch. This is why if you put water on your finger, so your finger is wet, you can pick up crumbs from a tabletop much more easily than you could if your finger were dry. Adhesion means that water molecules stick to other things, often because of hydrogen bonds, and this is why ammonia, for example, which is a gas, can go into water solution because it forms hydrogen bonds with the water molecules. If there were no hydrogen bonds, ammonia would not be very soluble in water. And that's good news and bad news. The bad news is you do not want to clean things with contact lenses in your eyes. If you're cleaning them with strong ammonia, the ammonia will end up going to solution in your eye, and your contact lens will stick to the cornea and you'll rip it off of your eye. And if that sounds awful, it is. You do not want that to happen. Okay, water also has a really high specific heat. That's very important, and a high heat of vaporization. Both of these are unusual characteristics. It has the second highest specific heat of a liquid at room temperature. The only, I think the only one higher is mercury, although it is very high though. And the reason this is good is because it makes water very effective for thermoregulation. Water can receive a lot of energy and not really change temperature very much at all. And this is important because you don't want your body temperature fluctuating greatly. It would be adverse on the chemical reactions in your nervous system. We thermoregulate, we keep our temperature relatively constant, and I'm sure most of you know that if you run a temperature, things don't work as well as they normally would. If you become hypothermic, they can become dangerous. And you can see this, I'm sure some of you have had this experience at home. If you take a large pot of water, put it on the stove, turn it on high, it doesn't boil instantaneously. It takes a long time for the water to warm up. The heat of vaporization is very important because it helps us cool off when we perspire. So if you have water on the surface of your skin, the water will evaporate. It takes energy from your body to evaporate that water, and you cool off. And I'm sure you all are aware of that. If you get out of a swimming pool and it's windy, regardless of what the surface temperature of the air is where you are, you will feel cold because the water evaporates. Another good thing about water is that it's a lubricant. We use this lubrication within the body cavities in the thoracic, in the abdomen, in the pelvis. Fluids between organs prevents friction. Friction is never a good thing. You end up with abrasion of the tissues. So lubrication is very important. We have pleural fluids, we have peritoneal fluids, and we also have fluids within your muscles, and they keep the muscles from abrading each other. Water is a good shock absorber. The primary place that we have shock absorption from water, the really most important one perhaps, is within the central nervous system. We're going to have the cerebrospinal fluid. It surrounds the brain and the spinal cord, and it prevents the brain from banging into your skull, at least with changes in your speed. This usually is not a problem. Under extreme conditions, it's not adequate, but for normal speeds that people move, typically this works out real well. Same thing for your spinal cord. And then we also have shock absorption in the bursa. Some of you have undoubtedly heard of having a bursa in your shoulder, or bursitis, something of that sort. And these are basically sacs filled with a fluid, water-based fluid, that can absorb shock so that the organs on either side of the bursa don't get damaged from physical impact. Acid and bases. So when I was putting together the chemistry lecture, I taught chemistry for about 35 years at URI, and I understand that that you really, I don't want to go in too deeply, but all these things again that I'm bringing up are important in our bodies. So we'll keep this to a minimum, but there are some pretty important things here. If you take pure water and you were to carefully analyze what is in the water, you would find that some of the water molecules dissociate or break down, and they give off a hydrogen ion which combines with another water molecule and a hydroxide ion. And because there are equal numbers of each of these, the water would be neutral. Not too many water molecules dissociate like this, And this is because that the forces within the molecules are very strong and they hold the atoms together. But there are some things that do break down. For example, carbonic acid. Now again, this is not a random acid that I pulled out. This is one that occurs in your body. And it occurs in your body whenever you have carbon dioxide and water, which is pretty much all the time. And carbon dioxide and water will actually interact and form carbonic acid. And it turns out that this is one of the major ways that we carry carbon dioxide in our blood. There's even an enzyme that speeds up this reaction. And we'll be talking about enzymes before awfully long, so if those of you who are not familiar with them, we will talk about that topic. But carbonic acid is a weak acid. It dissociates into hydrogen ions and bicarbonate ions, and it has some real importance within the body in terms of regulating the pH of your body. It also is the way that the glands in your stomach form hydrochloric acid for digestion, and the gland in your pancreas also uses this reaction to form sodium bicarbonate to neutralize the acid coming from the stomach into the duodenum. So this is a big deal, in addition to the fact that it's part of the major buffer system within the body. So this is a really important weak acid. We do have it throughout the body. Bases will combine with a hydrogen ion, or they will release a hydroxide ion. We don't have a lot of bases in the body, but one that we do have, and which is very important, is sodium bicarbonate. And sodium bicarbonate dissociates. Sodium salts generally dissociate pretty easily. And the bicarbonate ion that is released in the dissociation of the sodium bicarbonate, the bicarbonate ion will combine with hydrogen ions to form carbonic acid. And this is really an important weak base. It's the counterpart to the carbonic acid. So it's a carbonic acid sodium bicarbonate buffer system. Dissociate is actually a word I've been throwing around here, so maybe it's not clear, but if you think about if you break that word down, dissociate just means that two things, instead of remaining associated and together, sort of separate. Sort of like breaking up with your girlfriend or boyfriend. So both of the examples I gave here are weak acids and weak bases. We do have one strong acid in the body, that's hydrochloric acid. We'll talk more about its formation when we get to digestion, only briefly, but it is an important acid in digestion because it has a number of functions in the stomach. Okay. So when acids and bases react, typically if it's a strong acid and a strong base, they form a salt and water. For example, we have hydrochloric acid and sodium hydroxide. There's a strong acid and a strong base, and when they react, sodium chloride forms and water forms. And it doesn't back up. I don't know if you've noticed, but some of the arrows we've had in these reactions go both ways. This only goes to the right, basically goes to completion. So measuring acidity turns out to be pretty important. It's one of the parameters that doctors and scientists measure in the body and in the blood to see if things are normal. And if you get outside of normal pH, things don't go well. So there was a scale, and the scale was proposed a little bit over 100 years ago by a scientist called whose name was Sorensen, and he suggested the scale be called pH, and pH is equal to minus the log of the hydrogen ion concentration, which is basically equal to the log of the inverse of the hydrogen ion concentration. You do not need to know this. I'm just giving you a little bit of, this isn't just some made up value. The lower the pH, the more acidic a solution is. The higher the pH, the more alkaline the solution is. And so if we have a pH of 7.0, the solution is going to be neutral. And here is the scale. A pH of 14 would be the strongest possible alkaline solution, and a pH of 0 would be the strongest possible acidic solution. And so this scale is kind of a neat one to look at because it has some things on here that you either are familiar with or we'll talk about during the course. The stomach acid, very acidic, not at 0, but it's really quite acidic. Colas tend to be somewhat acidic, and you might ask why. Sometimes students think that this is about preserving them and preventing them from deteriorating, but Pansy knows the answer. Why a cola is acidic, Pansy? Right, they taste better. They're sort of tart. Oranges, tomatoes, these are all acidic. Urine tends to be acidic. The average urine is in a normal individual, if they're healthy and they aren't having any dysfunction, should be around 6.0, although it swings both positively and negatively from there depending on what's going on in your blood. Pure water should be 7, that would be neutral. Blood is mildly alkaline, between 7.35 and 7.45 typically. Baking soda, which is a bicarbonate, a little more alkaline. Seawater is quite alkaline. This actually is a problem for us today because with the greenhouse gases that are being put into the atmosphere, carbon dioxide is one of them. The carbon dioxide actually causes the water to become more acidic, right, because of the carbonic acid. And a shift in seawater pH can kill the organisms that live in the ocean, which is not desirable. Milk of magnesia, some of you may have taken that, which affects your gastrointestinal tract. Ammonia is really quite alkaline. Okay, so I'm going to show you a link here. Ooh, there's my email. Wow. Okay, so if we increase the H3O, which is basically the same thing as the hydrogen ion concentration, the material becomes more acidic. If we increase the hydroxide concentration, it becomes more alkaline. The pH increases as the alkaline nature increases, and you don't really have to worry about pOH, but it's basically the inverse of the pH, and as that increases, it becomes more acidic. Okay. So, pH scale. Acidic solutions are going to have more hydrogen ions than hydroxides. And alkaline solutions have more hydroxides than hydrogen ions. When we go from one unit to another of pH, we actually are changing the concentration of the hydrogen ions by a factor of 10. So if you go from 7 to 6, you have 10 times more hydrogen ions than you did at 7. If you go from 6 to 5, 10 times more than at 6. And obviously 100 times more than at 7, and so on. So it's sort of a logarithmic scale. In the body, if your pH goes below 7.0 or above 7.7, chances are if it doesn't get resolved quickly by your organ systems, it will kill you. It will cause you to be dead. Okay, so a normal pH of arterial blood about 7.4. If you have below 7.35, you're considered to be in acidosis, and if you have above 7.45, you have alkalosis. Neither of these are desirable. These, you're probably thinking, well, how can they come about? Actually, gastrointestinal disturbances can cause a shift in pH, depending on whether you're vomiting or whether you have diarrhea. We'll talk more about that when we get there. There's also metabolic shifts. Depends on what chemical events are happening in the cells. You can have kidney dysfunction that can usually causes acidosis. So each of the different organs can have an effect on that in some cases. We basically regulate our pH by way of several things. The main one is the kidneys. Kidneys are the most important in helping us balance our pH. The lungs, they're a secondary. They're pretty important because they're a way of getting rid of carbon dioxide, and carbon dioxide, you'll remember, reacts with water to form carbonic acid. And then we have buffers in the blood. We'll talk a little bit about buffers. Buffers are basically a way of stabilizing the pH so that it doesn't get out of hand. So, a buffer is going to be a substance that releases hydrogen ions when bases are added and bonds with hydrogen ions if you have acidic materials being added. It sort of keeps things near the middle. It reduces the change in the pH. So, for example, and this is one that's important, it happens in your duodenum. Your pancreas is going to secrete sodium bicarbonate into the duodenum, and it is going to combine with the hydrochloric acid coming from your stomach, and it neutralizes it by forming sodium chloride, which is just table salt, and carbonic acid. So this hydrochloric acid is a strong acid, carbonic acid is a weak acid. And carbonic acid can break down into carbon dioxide and water, so you can even get rid of the CO2 and end up with neutral water. It's a pretty ideal situation. This is the most important buffer system in the body. Okay. So, as I mentioned, in that reaction, we go from a strong acid to a weak acid. This keeps our pH from shifting significantly, and the importance of that is that the shifts in pH change the shape of proteins. Enzymes are proteins, and if you change those shapes by exposing them to the wrong pH, it denatures the protein, and the protein is never the same and doesn't function the same as it used to. So it's a way of actually inactivating an enzyme. This is what we do with pepsin coming out of the stomach. It gets deactivated, I guess, when it gets to the duodenum. I mentioned this, the carbonic acid will spontaneously form water and carbon dioxide. See, the arrow goes both ways, so this is reversible, but we can breathe the CO2 out, and when we do that, we end up with a neutral solution. So that's really an ideal system. Next, we want to talk about electrolytes, and I'm sure you've all heard of electrolytes. You know, you got to keep your electrolytes balanced, or your physiology gets kind of messed up. Electrolytes tend to be ionic compounds, and they go into solution in water because the water is polar. I remember, and so they actually kind of fit in between the water molecules. And it's called an electrolyte because if you put an electrolytic solution in where you have a potential electrical current, the solution will conduct the electricity. This is why people get electrocuted. You get an electric current will run through your body. The ions come from ionic compounds like sodium chloride, and the water breaks those ionic bonds so that they go into solution. And I mentioned already, electrolytic balance is really important for good health. If you're electrolytic imbalance, if you get electrolytic imbalance, you can have mental abnormalities in thought processes and problems conducting impulses through the body. We use those impulses to control our muscles and organs. We'll talk about impulses later on in the course. About 65% of our mass is inorganic, yet you probably thought you were an organic creature. Well, remember that 60% of your mass is water, and water is inorganic, so that's the big part of it right there. Most of our inorganic materials are small covalent compounds, such as water, or ionic compounds, such as sodium chloride. And in many cases, most cases, the inorganic compounds will form solutions. Now, there are some inorganic compounds in our bodies that do not go into solution. Actually, fortunately, for example, hydroxyapatite, which makes up your bones, the calcium phosphate, it's an inorganic base, and it's not very soluble. If it were, your bones would all dissolve and you wouldn't have them. The electrolytes are involved in electrical functions, and you probably never really thought of yourself as having electrical activity in your body, but basically you do. That's what you make use of when you have nerve impulses travel along nerves. And inorganic compounds also important in support against gravity through the bones. We'll talk more about those as well. Water is inorganic. We already talked about that. When we write something like H2O, that's considered a molecular formula. Then these may not be familiar with you, or to you, but they will be, I hope, by the end of the course. Na is sodium. That's a sodium ion. It has a positive charge, which means that did it gain an electron or lose an electron? Pansy. Right. It lost an electron. K is for potassium. Okay. S is sulfur. Sulfur tends to form a -2 ion, sulfide. Chloride, Cl, right? Sodium chloride is table salt, at least most of it is. Fe2, iron. Okay, iron's a really important inorganic material incorporated into hemoglobin. So we have organic compounds, molecules of life, and the polymers have a number of subunits that are all combined together, and then the subunits are usually referred to as monomers. Poly means many, and mono means singular, right? A single one. So some of the organic compounds that we have within the body are going to include carbohydrates, lipids, proteins, and nucleic acids. Those are the four main categories. We're going to discuss each of those a little bit. And all organic compounds have carbon and hydrogen in them. And they often have other elements as well, but carbon and hydrogen are sort of the foundation. And usually they're fairly stable. Not perfectly stable, so they can break down, but usually they're fairly stable. And the fact that carbon forms 4 bonds is a really big deal, because it means that there's a potential for a huge amount of diversity, and millions of compounds featuring carbon have been identified. I mentioned there were other elements often found in organic materials. The other elements that typically are found are oxygen and nitrogen, and sometimes sulfur. So these cells in your body manufacture or synthesize. Usually when we're talking about the cell activity, we would say they don't manufacture compounds. We'd usually say they synthesize. Synthesis is just a manufacturing of compounds. It's a fancy name for that. And what the cells typically do is they put subunits, the monomers, together with a dehydration action or a reaction to form the polymers. And dehydration, as the name implies, is you're taking water out, right? So when you remove water, that's a dehydration reaction. Cells also sometimes break down macromolecules. And when they break them down, it's usually done with a hydration reaction. And hydration means you add water. And they break these polymers, macromolecules, down into monomers. So there's a potential to go in both directions on that. We'll start with carbohydrates. All carbohydrates have carbon, hydrogen, and oxygen, and typically the ratio of hydrogen to oxygen is 2 to 1. Now, it doesn't mean that you have a water molecule. It just means that for every hydrogen or for every oxygen, there are 2 hydrogens, and that's where the hydrate comes from. Functionally, carbohydrates are really important for us, and the reason is carbohydrates are typically the energy source in all cells. Now, if you are deficient in carbohydrates, your cells can metabolize other organic types. You can metabolize proteins and they can metabolize fat. So if you went on a starvation diet or were put in a situation where you were starving because you couldn't get any food, your cells will start using other things for energy source. But typically, carbohydrates are first choice. So when you break carbohydrates down, you get energy, you get carbon dioxide, and you get water. And that would be the case if we were breaking down glucose, for example. We're going to talk way more about that. Unfortunately, not all the energy gets trapped or used, but we can use a fair amount of it. Many, but not all, carbohydrates are soluble in water. And that's good because, remember, we transport materials within the body by using the blood, and that's going to require these things be soluble. So some simple carbohydrates. The monosaccharides are the simplest sugars. Glucose, for example, has 6 carbons. Hexose is another example. Typically, the monosaccharides have between 3 and 7 carbon atoms. Fructose and galactose are also a type of monosaccharide with 6 carbons. Okay, hexose just means 6. Here is a model of a carbohydrate, specifically glucose. And so sometimes we have disaccharides. Now, you know the word di, or the prefix di. Pansy knows what di means. Pansy, what does di mean? Right, 2. Actually, sometimes Pansy doesn't bark. Sometimes she just moves her paw. But in that case, she enunciated di pretty well. Or 2, rather. This is going to be when 2 monosaccharides join through a dehydration reaction. Here are a couple of examples. Maltose is a disaccharide. It forms when you take 2 glucose molecules and combine them. We have sucrose. Sucrose comes from a combination of glucose and fructose. Table sugar is sucrose, just as a point of information. We have lactose. Lactose forms when glucose and galactose come together, and lactose is found in milk. Some people can't digest lactose, and those people are referred to as being lactose intolerant. Typically, if you're lactose intolerant and you consume material with lactose, you'll get cramping and diarrhea and other gastrointestinal distress. Complex carbohydrates are important. Polysaccharides, for example, are made up of many glucose molecules strung together. And plants, when they have excess energy, actually store most of their excess energy as starch, which is a polysaccharide. We do not store starch, but we do store glycogen. And glycogen is a polysaccharide. It's not exactly like starch, but you know, if you think of it in a grand terms, it sort of is. It's many glucose molecules put together. And glycogen is stored in minimal amounts in 2 places. Skeletal muscle cells tend to store a certain amount of glycogen, and so does the liver. Usually you have about enough glycogen to get you through 1 day worth of activity, or about 22 miles of a marathon. And what happens when people get to about the 22-mile mark in a marathon, Pansy? What is it called? Right, the wall. They hit the wall. When you hit the wall in a marathon, it's because you've run out of glycogen, and your cells have to start metabolizing other organic molecules to get the energy. Isn't that Pansy is wicked smart? Blood glucose levels typically around 0.1%. If the blood glucose gets below that, the liver is stimulated to release glucose into the blood. And if you don't have glucose immediately available, which is usually the case, the liver can take glycogen and break it down into glucose molecules, and then they can be added. There's actually a hormone that comes from the pancreas called glucagon. Glucagon, and glucagon stimulates the liver to form glucose from glycogen. Blood glucose levels are really important for normal brain and nerve function. If your glucose levels drop too low, your brain starts to dysfunction. And brain and nerve tissue usually use glucose for energy release. Now, in order for this to work properly throughout the body, you need an enzyme called insulin. Some of you are probably aware of that. And if an individual is deficient in insulin, the glucose doesn't get used, and the glucose levels build up in the blood, spill over into the urine, and this is referred to as diabetes. Cellulose is a polysaccharide, and cellulose is a polysaccharide produced by plants. We do not have the enzyme that digests cellulose, so if you consume cellulose, cellulose is known as what in normal layman's terms, Pans? Right, fiber. Right? Fiber in your diet. Fiber is cellulose. We can't break it down. It does have a really important function in the gastrointestinal tract, and we'll talk about that later on in the course. Okay, lipids. Lipids have more energy per gram than carbohydrates or proteins. And because of that, it makes a really great type of molecule to store energy for animals. So the obvious question is, and this comes to sort of an overriding principle of evolution, we tend to have things the way they are because they have advantages. We'll talk a little bit more about that later in the course, but advantageous properties tend to be passed on, and the organisms that don't have those properties tend not to be as successful. So the obvious question is, why, if plants store starch, why don't we store starch? Why do we store lipids? And the two advantages that lipids have is that they're lightweight, and you can figure this out. If you take a pound of cornstarch, it has 1,729 calories. If you take a pound of fat, it has 3,500 calories. That's pretty close to a 2-to-1 ratio. So if you have a pound of fat, you're storing twice as much energy as if you have a pound of starch. That means that we would be lighter, storing the same amount of energy. And lipids tend to be more flexible. So the obvious question is, okay, so why are these important? We're going to see throughout the course that one of the really important things for our well-being is that we have speed. Animals need speed for one of two reasons. So this is the first time we've talked about this, but it'll come up again. Why would animals need to be speed? For example, Pansy, why is it important for you to be fast? Right, to catch rabbits. Right, so if you're a predator and you want to catch a prey organism, you have to be faster than it or smarter. But in Pansy's case, she has to be faster to catch those rabbits. And so why would a rabbit need to be fast? Right, to get away from Pansy. Oh my goodness, she got this all figured out. So another principle that we're going to find out, or reality, is that whenever there's an advantage, there is a disadvantage. You never get a free lunch. There's always trade-offs. And the trade-off with lipids is that they're not very soluble in water, which is a problem, right? Because we use water to transport things through our body. So the obvious question is, why are lipids not soluble in water? And the answer is because they're nonpolar in their covalent bonds. So the water, they're hydrophobic, and the water and fats don't mix. You've seen this, I'm sure, if you've ever tried to wash a plate or clothing. If you get butter all over your clothing, it's really hard to get the butter out if you just pour water on it. In fact, pretty much you can't. You have to use soap, right? Because the water are polar molecules and the lipids are nonpolar and they don't mix. Okay. Oh, so then you might ask, well, how do we carry them in the blood? Typically, we have other molecules that act sort of like soap and attach to the lipids and are water soluble, and they just kind of carry the fats along with them. There are some vitamins that are lipid soluble, and four important ones that are vitamin A, D, E, and K. Not all vitamins are lipid soluble. Vitamins B and C are water soluble. So you tend to find lipid soluble vitamins stored in fatty tissues if there's excess of them. Lipids are mostly carbon and hydrogen. They have some oxygen. Sometimes they have phosphates. The ones that have phosphates are called phospholipids, and they actually are pretty important. A normal healthy individual has somewhere between 12 and 27% of their mass made up of lipids. Some people have more than that. More is usually not beneficial. Most of the fats that are formed by animals are solid at room temperature. If you've ever purchased a piece of meat or something at a grocery store and it has fat associated with it, you can see these pieces of white material within the mass of meat that you bought. On the other hand, plants typically have lipids in oils. They tend to be liquid at room temperature. So what about the functions for fats? Well, they have three major functions. Energy storage, that's a real big one. Because as we've already said, most of your energy storage is done with lipids. Insulation against heat loss or impulses spreading from nerves. So the insulation against heat loss you can see in marine mammals. Marine mammals have something called blubber, and blubber prevents them from dying of hypothermia. That's a really big deal. Also, if you look at nerves running through the body, they tend to look sort of white, and that white material associated with the nerves is actually lipid material that insulates the nerves, much like the wires of your computer cord, charging cord, have insulation so that you don't get electrocuted when you pick them up. Also, we use lipids as cushions around a lot of the organs too, and this helps and reduce the likelihood that you're going to have damage from impact or something like that. So most excess food is converted into neutral fats for storage, and this turns out to be very useful. Most animals, with the probable exception of humans, spend most of their lives trying to get enough food so that they don't starve to death. And so if they get the opportunity to get extra food, they convert it into fats, they store that fat, and then it can be used in the future if things get kind of on the thin side in terms of their food intake. The neutral fats are the way we store things, and they are the most abundant of our lipids. So emulsification. You remember that I said that fats aren't very soluble in water. This is a problem in our blood. It's also a problem when we're digesting things. If you eat fatty material like ice cream, for example, the fats in the ice cream don't interact very well with the watery solution in your gastrointestinal tract that contains enzymes and the other things necessary to break them down. So we need to emulsify the fats, sort of like what you do with a plate that has fat on it and you want to clean. You put soap on it. Soap is an emulsification agent. Okay, and so it reduces the surface tension of the water and allows these lipids to go in between the water molecules. Basically, the emulsifying agents, some of them are found in bile, for example, combine with the lipids and then make them soluble in water. Not actually soluble. Sorry, they don't make it. They emulsify it. So the lipid doesn't actually combine with the water; it just kind of slips in between the water molecules because of these emulsifiers. Okay. Saturated fats. You've probably heard of saturated and polyunsaturated foods. When we have fatty acids, they are formed by carbon chains, and fatty acids have a carboxyl group at the end, COOH. So there's a double bond between one of the oxygens and the carbon, the other has a single bond to the OH. Saturated fatty acids tend to be solid at room temperature, and they have a lot of hydrogens associated. You see that all the carbons have hydrogens except for the one end where we have that COOH. We also have unsaturated fatty acids. Those are the ones that are usually considered a little more healthy if they're part of your diet. And here, instead of having the carbon saturated with hydrogens, there are actually some double bonds within the molecule, and these tend to be more liquid at room temperature. So I'll give you, I think I have a model of one. Here we go. Here's an unsaturated fatty acid. So you see that there's a double bond here. If it were saturated, there'd be a hydrogen here and a hydrogen here. This is not polyunsaturated. This is just an unsaturated fatty acid. Polyunsaturated means there would be many of these double bonds. The more of the double bonds, the more oily and the less solid the material will be at room temperature. So you can make unsaturated fatty acids into solids. And you might think, well, if the saturated ones aren't good for us, why would we do that? Well, it turns out that cooking is done a lot more effectively with saturated fats than unsaturated fats. They tend to evaporate less easily, and in a cooking situation they tend to stay as a liquid. So basically you treat these molecules so that you break the double bonds and replace the double bonds with hydrogen atoms. Okay, icosanoids are modified fatty acids, and we're going to talk about them later in the course. They are used in communication between cells, and prostaglandins, which is one of the materials that we use to communicate, are icosanoids. We will talk more about those. They occur at very low concentrations, but they are very important for a number of physiological activities. One of the things that we'll see throughout the course is that there are different ways of communicating between cells. So one way of communicating is using chemicals like icosanoids or like hormones. Another way is using nerves, and we'll draw the distinction between those when we get to that. Phospholipids. Phospholipids are really important. These are lipids that have phosphate groups associated with them, and a phosphate group typically will attach somewhere along the molecule. Sometimes we have groups that include both phosphate and nitrogen, and the phosphate interacts with the water, and that's really important in cell membrane structure. We find that the cell membrane is a series of phospholipid molecules that are associated with each other, and the phosphates tend to face toward the water side of the membrane, and the non-phosphate or hydrophobic portion tends to be in the middle of the membrane. So the membrane is made up of a bilayer. There are a set of phospholipids outside and a set of phospholipids inside, and as I mentioned, the phosphate group interacts with the water both on the inside and on the outside of the cell. The fatty acid tails, which are hydrophobic, they're non-polar, and they tend to be in the middle of the membrane. So here is a model, a drawing of a model of a cell membrane. We have the phosphate groups here, these little round ball things, right? And then the fatty acid portion in the middle. And the water is out here, and the water is out here. So water interacts with the phosphates. It would not interact with the hydrophobic tail. Okay. Steroids. I'm guessing most of you have heard of those, even if you don't know much about chemistry. But steroids have a carbon ring, 4-carbon ring, as the backbone of the molecule, and then they have side chains, and these attach to the rings and determine what exactly the molecule will do. Cholesterol is a steroid. Now, cholesterol gets kind of a bad rap, but it's a pretty important molecule in a lot of ways. You need cholesterol to be healthy, at least a certain amount of it. And cholesterol is incorporated into the cell membrane, and it also is a precursor for the formation of vitamin D. Vitamin D is important for bone health and development. Some hormones are steroids, and if you watch professional sports, I just said baseball and football, but it turns out there are other sports where steroids have been used. Track and field, swimming, all sorts of sports where strength is required. Anabolic steroids make it possible for people to be stronger, and I guess that's good news, but it also has some bad news. One of the things is it reduces sperm production in males. In females, there are a number of unfortunate side effects. Facial hair usually increases Their voice usually deepens, breasts become smaller, mammary glands, and menstrual cycle becomes irregular. Some more unfortunate side effects. It lowers the good cholesterol in your blood, which has been suspected of having adverse effects on your health of your blood vessels. It raises blood pressure. That definitely has adverse effect on your health. And it also, in some people, causes aggressive behavior. Another unfortunate thing is that people who take steroids, between 14 and 57% of them become addicted. And steroid use was outlawed back in 1991. You might think it still is sort of done on a black market, and in fact it is. And it's not unusual at all to find that sports figures are using these illegally, and usually doesn't end well for them. Just as a point of information, so not to be pontificating here or anything, but you're better off not using steroids to build up body mass. You'd be better off doing that naturally. Steroids, the cholesterol is a steroid, as I said, and has these rings, carbon rings. This is a structural formula. That's a space-filled model. Cholesterol does have some good news associated with it. It's used as a precursor in building all three major sex hormones: testosterone for males, estrogen and progesterone in females. And mostly these sex hormones are produced by the gonads, either the testicles or the ovaries. But some precursors for these sex hormones are also produced by the adrenal glands. So proteins are next. Proteins have lots of functions. Hormones are proteins. An example would be insulin. And I think if you check, I've just prepared the copy of this PowerPoint for your class. You'll see that the specifics here are left blank. You might want to be filling these in. Muscle contractions based on proteins. Transport of molecules in the blood. Transport molecules are often proteins. For example, hemoglobin is a protein. Transports both carbon dioxide and oxygen. Antibodies are proteins. Enzymes are proteins. Collagen is a connective tissue protein, very important in stabilizing connective tissues, including bone tissue. Myoglobin is similar to hemoglobin. You can see kind of this globin thing here. Myo means muscle, right? So myoglobin is found in muscle cells, and that's a protein. I already mentioned antibodies. So proteins are macromolecules. These are polymers. They're large molecules. Typically, they are synthesized, made by the cells in our bodies. And the basic building blocks for proteins are called amino acids. And they're put together not unlike the letters that you would use to form words. There are 20 amino acids that our cells use. And all amino acids have two kinds of groups. They have an amine group, so CH3 with a nitrogen and two hydrogens associated with it. Well, actually the CH3 is not the amine part, the NH2 is. And then carboxyl groups, and a carboxyl is this carbon with a double bond to oxygen and a bond to hydroxide. And I'd already mentioned these before. That's the carboxyl group. Okay. So I mentioned that we form these proteins by combining these things. Here we have the amino group coming in here, the carboxyl group coming in here, and here we have some side chain, and the R is just an undefined side chain of carbon bonded to other things. So the amino acids are going to differ. Now, as I said, there are 20 different ones of them, and they are joined together by peptide bonds. So proteins are end up being polypeptides, many peptide bonds. Here's an example where we form a peptide bond by combining two materials or two monomers. And you see right here we have an O, an H, and an H. When these things combine, this is a dehydration reaction, and the water is given off, H2O, and I think that's left blank for you there. That was a peptide bond forming. So the what exactly the protein is will be determined by the order of the amino acids in it, a lot like spelling a word, as I mentioned before. So a good example is hemoglobin. Hemoglobin has 514 amino acids. That is a lot of individual building blocks. It's not the largest of the proteins that we have, but it is a substantial molecule. And those building blocks have to be in the right order. If there is a mistake made when the amino acids are being put together, you end up with an abnormal protein, and it doesn't do what it's supposed to do. And a good example, simple example to show you is the word one, an O, an N, and an E, neo, N-E-O. It has the same letters. It means a very different thing than one, right? So neo means new, different word. So the same thing happens when you're putting proteins together. If the amino acids get out of sequence, you end up with an abnormal protein. A good example of an abnormal protein that has rather dramatic effect on some people's lives is people with sickle cell anemia. Their hemoglobin has one mistake out of the 514 amino acids, and they end up with a hemoglobin that is deficient in oxygen carrying capacity. Another thing that I've used for a long time to try to give you an analogy of how these things go together is pop beads, just a little more visual. So let's say that we have 20 amino acids. So imagine that you had a collection of pop beads that were in 20 colors and different shapes. And so here's an example. Here we just have 4 types of pop beads, but we have one sequence here which is different than this sequence, and which is different than this sequence, which is different than this. So each of these would be a different molecule. Proteins are sort of like this. Here's another example with 20 different colors and shapes, and so we can have much more. Actually not 20. This one has 11. Imagine that we had 20 though. You could really get quite a variety of proteins formed from those pop beads, right? The amino acids. The order of the amino acids is a primary structure. Now, normally I wouldn't go through these structures except that there's kind of an important piece at the end, so bear with me on this. We have this primary structure, which is basically the order, just like the order of a word. You could spell that out. But then the protein molecules tend to fold or coil, and this is a secondary structure. Hydrogen bonds are responsible for this coiling of the proteins. And then we have a tertiary structure. Tertiary structures happen because of the side branches that are not the carboxyl or amine groups. And these are going to result in the hydrophilic portions of the molecule being on the outside so it can react with water, and the hydrophobic portion of the molecule being on the inside, so that isn't a problem for the water because the water doesn't get exposed to that. And the key thing here, and I think this is left out of your slide, this makes them soluble, and solubility is a big deal if we're going to transport them. Lastly, we have a quaternary structure, and if there are more than one polypeptide. And so, for example, hemoglobin has 4 protein subunits, and so it ends up with a quaternary structure. So why? So why are we bothering with these levels of structure? The quaternary structure can be changed by either heating the protein up or subjecting to it a change in pH. And when that happens, the shape of the protein changes. That's called denaturation. You can see this when you cook an egg. So if you look at egg white is almost all protein. And if you put it in the pan and you heat it up, it turns white and rubbery. And if you cool it off, it doesn't go back to being what it was before. So you've had a permanent change in the nature of the protein. If that were an enzyme, the enzyme wouldn't work anymore. It would have been deactivated, and it would just not have any digestive properties any longer. So it's a permanent change. When you change the shape, you lose the function. And this is another case of shape and function being associated with each other. Okay. So the example that's really important for us, one example, is pepsin. Pepsin is a strong proteolytic enzyme. It breaks down proteins, and it is formed in the stomach. And it only is active in a low pH environment, which the stomach has. When it goes into the duodenum, fortunately for us, it gets neutralized by bicarbonates that are secreted from the pancreas. If that were not to happen, the pepsin would digest your duodenum. You'd end up with duodenal ulcers, and it could result in severe symptoms, perhaps even death, depending on how bad it is. So denaturation also causes, or is believed to be, a contributing cause to Alzheimer's disease. So let's look a little bit at enzymatic reactions. Proteins form enzymes are usually proteins, and enzymes are organic catalysts, and what that means is they alter reaction rates. Almost always proteins, and one of the keys here is they don't make reactions happen that wouldn't happen anyway. So for example, you couldn't take mud and pour enzymes on it and make it into gold, because that wouldn't happen even if there were no enzymes there. But it does speed reactions up, and it actually, if you have a reaction that's reversible, it speeds it up in both directions. This is very important. Remember doing physiology a long time ago with a textbook, and the example they used was that if you ate a normal dinner, it would take you about 50 years to digest it if you didn't have enzymes. And obviously, we don't have that long to wait. They're very specific on what they work on, and this is because of their shape. Lock and key example is that if you have a key, for example, one for my truck, it doesn't work on any of my cars, or my house, or my office, or any other lock, except maybe on another truck just like mine. And this is because of the shape of that key. Okay? And if you change the shape of that key by taking a pair of pliers and twisting it, it doesn't work on my truck either. So enzymes fit against a reactant. This is that form, the importance of form and shape. And when they do, they combine sort of loosely, so this is called an enzyme substrate complex. The really nice thing about enzymes is that they get recycled. They get released after the reaction. The enzyme is unchanged by having the reaction occurred, and so it means that it's sort of an energy saver, because you can recycle these things. You don't have to get new enzymes for every time you want to have a reaction occur. You can reuse them. Some enzymes require cofactors. Some of you have probably heard of cofactors, inorganic coenzymes or vitamins. And so some of you may have heard of Q10, CoQ10 rather. That's a coenzyme that's important in lipid management within the body. Many times what enzymes do is they lower the activation energy. I'm going to show you an energy diagram for a reaction in a moment here. But by lowering that activation energy, it speeds the reaction up, because more molecules have enough energy to react. So here's an example. This is an energy diagram. So here's the amount of potential energy we have here. We have some reactants up here with a certain amount of energy, and this would be like a car on a hill. So if you want this car to go down the hill, you have to push it over the speed bump. The speed bump is the activation energy, And when the reactants get this much energy, they'll react and they form products. And in most cases, the products will have less energy than the reactants. This is what kind of a reaction? Pansy knows this. Right, exothermic. So exothermic means that energy is given off. Okay. What kind of reactions do we have? We have synthesis reactions. In synthesis reactions, reactants come together to form reactants come together to form a larger molecule. Typically, when you have two reactants coming together to form a larger molecule, it's an endothermic reaction, which means that it requires energy. It's like building a car. If you're building a car, it takes energy to be able to do that. We have degradation or decomposition reactions. In this case, what happens is the macromolecule or polymer is broken down into two or more products. Digestion of molecules by enzymes in your gastrointestinal tract is an example of breaking molecules down. And by the way, why would we need to break these molecules down? Anybody have an idea? Right. You have to break them down because they're too big to get through the membranes that line the gastrointestinal tract. Sort of like having a grand piano outside of a door. If you want to get the grand piano into the room, you can do so by taking it apart instead of destroying the house. So an example of degradation would be the breaking down of glucose within the cell to get energy that we can use to do cellular activities. Replacement reactions or exchange reactions. An example would be a reaction of an acid and a buffer. We've already done one of those. So the sodium bicarbonate that you find in your duodenum reacts with hydrochloric acid from your stomach, and you get carbonic acid and sodium chloride. They've switched partners. The sodium has taken the chloride from the hydrochloric acid. The bicarbonate has taken the hydrogen ion from the carbonic acid, or from the hydrochloric acid, and you end up with carbonic acid and sodium chloride. This brings us to another category of organic molecules, very important ones, the nucleic acids. Remember, there were four. We had carbohydrates, lipids, proteins, and nucleic acids. And one of the main types of nucleic acids is deoxyribonucleic acid. This is made with a special sugar, a deoxyribose sugar. And the DNA is the basis for heredity. That's a big deal. The second kind of nucleic acid that we have are ribonucleic acid, RNA. And this function is directing activity outside of the nucleus in the cell. The RNA is synthesized from the DNA. So nucleic acids are made up of nucleotides, and each nucleotide has three components. It has a phosphoric acid, a pentose sugar, which is a 5-carbon sugar, and a nitrogen-containing base. So the DNA is like the blueprints for everything that goes on within the cell, and including making the RNA. DNA is the largest of all organic molecules, and it contains the genes. I'm thinking Levi's, maybe that's what I have. So genes are sort of like a recipe. They tell the cell how to do things. So the DNA is able to replicate itself. It's unusual in that case. RNA can't do that. The RNA always comes from the DNA. It makes the RNA, and the RNA is going to be essential for synthesizing proteins. And the DNA also controls the cell division. It is a helical molecule, and so some of you might not know what a helical molecule looks like. It looks sort of like a spiral staircase. So the recipes, those are the genes, are in the DNA, and if you think about it, if you want this cell to be successful when it reproduces itself, the recipes that it passes on, the genes have to be exactly the same as they were in the original cell. If they're not, then problems are going to arise. Now, does that ever happen? It does. Sometimes things are not passed on properly, and that's not unheard of. It usually doesn't end well. RNA is sort of like a photocopy of the DNA. There are some similarities and differences between them, and we'll go through those in a little bit here. The DNA contains deoxyribose. It's a 5-carbon sugar and 4 nitrogenous bases. And in the DNA, the purines are adenine and guanine, and the pyrimidines are thymine and cytosine. Now, I made the thymine red because when we talk about RNA, we're going to see that they also have, the RNA molecules also have purines and pyrimidines, but instead of having thymine, they have uracil. The other 3 are the same. So adenine always bonds with thymine, and cytosine always bonds with guanine. A purine always bonds with a pyrimidine. And to help me remember this, when I was in undergraduate school at URI, we used to race sailboats. I was on the sailing team, and we raced at Coast Guard. And if you can remember, at Coast Guard you have AT and CG. So adenine with thymine and cytosine with guanine. If you can't remember that, I don't know what to tell you. The 2 sides, or 2 strands of the DNA, are held together by hydrogen bonds in the middle. And, excuse me, the pairing of the bases within the molecule is going to occur because of their geometry. That's why the adenine always goes with thymine and the cytosine always goes with guanine. Because this is predictable, the sequence is always maintained when the DNA duplicates itself. So here we have a drawing of what we might have. This is obviously not twisted. I made it flat on purpose. We have a phosphoric acid. We have nitrogenous bases. One of these would be adenine, and the other would be thymine or cytosine and guanine. Or they could be the other way. This could be thymine, this could be adenine. And then we have the 5-carbon deoxyribose sugar. Here is a model, and here I think you can get the sense of the spiral staircase. And those hydrogen bonds are occurring in between the nitrogenous bases in the middle of the 2 strands. Okay, RNA is going to contain the ribose sugar. This is a mistake. It contains ribose sugar, not deoxyribose sugar. And the 4 nitrogenous bases here are going to be adenine, guanine, uracil, and cytosine. It's single-stranded. It does not make a helix, although sometimes it does kind of fold back on itself. And the RNA sequence is going to determine the amino acid sequence in the protein synthesis. It's the directions that the cell uses to determine which amino acid to incorporate. So the cell reads 3 nitrogenous bases in sequence, sort of like reading a zipper, and then it adds in the amino acid. One of the differences is that RNA, the uracil, is a nitrogenous base instead of thymine when that's used. So if we contrast DNA and RNA, and you'll notice, I think, when you look at the wish list of concepts that you're supposed to grasp, you'll see that contrasts are often mentioned there. You want to be able to say, well, this has this, while that has something different. So we have a ribose sugar instead of deoxyribose sugar in the RNA. I mentioned that a little earlier. There was a mistake in the PowerPoint. I'll correct that so your version will be correct. We have uracil instead of thymine. It's not as stable as DNA, so eventually it breaks down and you have to get new RNA made if you want to continue the activity that it directs. RNA is a single chain, although as I mentioned sometimes it folds on itself and doubles up. It's a shorter molecule than the DNA. And DNA is mostly found in the nucleus. RNA is found throughout the cell. DNA is the only one of the 2 that can replicate itself. There are 3 kinds of RNA. We'll talk more about those later on when we talk about protein synthesis by the endoplasmic reticulum. But we have messenger RNA, we have ribosomal RNA and transfer RNA, and we'll see that each of those has specific duties within the cell. Another extremely important molecule is adenosine triphosphate, or ATP. And adenosine triphosphate is a nucleotide, excuse me, and its function is that it transfers energy within the cell. So you can kind of think of it as a battery pack. When we synthesize ATP, mostly in the mitochondria, which is an organelle we'll talk about, it's sort of like charging the battery pack up. And then that battery pack is released, it goes throughout the cell, diffuses through the cell, and when the cell requires energy, the ATP can be split. One of the phosphate groups gets split off, and energy is released, and we use some of that energy to accomplish a variety of cellular activities. So the ATP is made up of adenine, ribose sugar, and 3-phosphate groups. So here's the structural formula. Here are the 3 phosphates right here. So what happens when you release energy is this group at the end here splits off, and you're left with ADP, adenosine diphosphate. Here's the reaction. If you take ATP and add water, that's a hydrolysis reaction. You end up with ADP, a phosphate group, and energy. Okay. And some of that energy can be used then. So this energy is being stored as chemical energy or potential energy until it's needed. So if you didn't have any ATP and you couldn't make it, when you broke down carbohydrates, the energy would be released as heat, and unfortunately our cells can't use heat to do things. So what do we use this energy for anyway, Dr. J? So Pansy knows. One of the things we use it for is chemical synthesis. Another thing we use energy for is transport through the cell membrane. And the last one, Pansy? Mechanical activity. Unbelievable. She's so smart. Okay, so chemical synthesis, building chemicals, mechanical work such as muscle contraction or amoeboid movement by cells, cilia moving in the cells, we'll talk about those, and then transport across the cell membrane. In some cases we actually use energy to make that happen. The energy is released when these molecules break down, and the energy that is released when you break down glucose, for example, some of it can be trapped. Usually between 36 and 40 ATP molecules are produced for every glucose molecule that gets degraded. And unfortunately it's not 100% efficient, so some of the energy goes off as heat. Actually a little bit more than half. That's why when you exercise you get warmer, because some of the energy you're releasing is just lost as heat and you can't really reclaim it or use it. So somewhere between 40 and 100% of the energy released, it gets into the ATP molecules. Mostly it's closer to 40%. The time that you can get 100% conversion is when you break down lipid materials. So that heat is good news and bad news. If you're cold, it's good news because it warms you up. If you're warm, it's bad news because if you get really hot, it can kill you. And that gets us through quiz 2. Hope you learned a lot, and I look forward to delivering this material to you in class. We'll have probably a little more discussion. Okay.